Hey guys, thanks very much for coming. My name is John Kodumal. I'm a team lead here at Atlassian. So I've been working on a project called the Atlassian Marketplace. And basically what we've been doing is we've been basically making an app store for Atlassian applications where you can purchase add-ons that third parties have made from within products like Jira. And how that becomes relevant to this talk is that as part of that project, we launched a new site called marketplace.atlassian.com. And we're actually going to be announcing that at our big user conference next week. That we got to pick a new tech stack for that. I chose Scala with Mongo on the back end. And one of the things that we wanted to do was try to be as functional as possible. We're big into pure functional languages and big Haskell fans amongst us. And we decided to use Scala Z, which is a library that tries to bring some of the concepts from Haskell into the Scala world. And we use Scala Z pretty heavily in this new marketplace.atlassian.com project. This was also a huge move for us because traditionally Atlassian is a Java shop. And so we were just getting started with getting a new set of developers acclimated to Scala. We had a core set of developers, 3 or 4 of us, who were already pretty familiar with Scala and wanted to take it to the next level to Scala Z. And then when we came out of a room a couple months later into the project and launched it on everybody, and we were like, hey guys, Scala is awesome. And they looked at the code and there were monads everywhere and monad transformers all up the wazoo. People got a little intimidated. And so what I thought would help would be a little training for the team. And I started looking, we started on chat when people would ask for help. I'd be like, oh yeah, just read this tutorial, and it would be something for Haskell. And there was like a lot of cognitive dissonance there because people would be like reading stuff and saying, okay, it works like this, and then the Haskell concept wouldn't apply very cleanly to Scala. And so that level of indirection I think was really problematic for people. So one of the things that I wanted to do was ditch that level of indirection. So I took one of the better tutorials that I found, one of the better pieces of documentation that I found from the Haskell world, which is called the Typeclassopedia, written by this guy named Brent Yorgi, and I decided to port it to Scala. And interestingly enough, I thought I'd just be sort of porting, making syntax changes and showing what the syntax would look like in Scala. And there was a lot of that, to be quite fair. But Scala and Haskell are very different languages. And they're different in ways that really matter when you're explaining this material. And so I found that I had to sort of redefine how things worked a little bit. Scala Z defines some of the types a little bit differently. There are historical mistakes in Haskell that have been corrected in Scala Z and mistakes introduced in Scala Z because of the way Scala works. And I tried to kind of sort all of that out and present a more unified document about this stuff. So this is the Typeclassopedia, the Scala version. And this is basically only the first third of the Typeclassopedia. So this is going to be a little bit of a short talk. So hopefully we'll have a time to chat afterwards. I'm intending to continue this and maybe do the second and third parts at some point in the near future. So let's get started, yeah? So the first thing that we need to talk about is what a type class is. So how many of you guys actually are Haskell refugees? Okay, so a couple of people. So this is going to feel like a warm and fuzzy blanket for you, right? It's going to be pretty easy, and I hope that doesn't put you off. I think that hopefully this will still be interesting to you. How many of you guys are heavy users of Scala Z, or have you used Scala Z at all in your code? Cool, so there's some people. And so this will be hopefully bringing some of the concepts in Scala Z and sort of documenting them for you, because a lot of Scala Z is it's pretty hard to learn, I think. Anyway, type classes. So the first thing that we need to talk about is type classes. But this is kind of just prerequisite material. I'm not actually going to spend an hour explaining what type classes are. Actually, Dan made an awesome tutorial on type classes, and I would highly recommend going online and checking that out if you want a little more detailed material. Dan says it's on YouTube, so it must be on YouTube. So let me just give you the brief 10-minute primer on type classes, and we'll move on from there. So type classes are kind of like, I call them open world interfaces. And they're kind of akin to Java interfaces, at least to a first approximation. But they're a little bit more flexible, and we'll see how that works in a second. So the main thing that I want to get across here is that I want to define a set of behaviors that a class or something like that must implement, right? And in the Java world, I would do that with an interface. The sort of Scala level version of that would just be to declare a trait. So like something like this. In this particular example, I'm going to declare a trait called show, and it's going to work kind of like toString. So I'm going to apply show to anything that I want to, say, print out on the REPL, something like that. Now, in the Java style of things, I would declare the show trait like this, or the show interface like this, where I would define the methods that I want my interface to implement, and then I would just define the methods. That's it, really. But in Scala, with a type class, there's going to be a slight distinction. And it's going to look like this. So instead of just having show, I'm going to add a parameterized type here. So this show will take a type parameter A. And I'll define the shows method as taking a value of type A and returning a string. But really, what I'm doing is the same thing. I'm defining a set of behaviors. That's the type class that I want my code to implement. So after I define the type class, I need a way to say that a particular type belongs to that class. And that's the second step here. So what I'm going to provide is what I like to call a witness. It's an instance of that type class for any particular type. And the way that's implemented in Scala is to basically make an anonymous class specialized to the type that you want to add to the type class. So in this case, I want to say that int should belong to the show type class. How do I do that? Well, I make a new show int. It's an anonymous class. And I implement the shows method. And in this particular case, all I'm going to do is call toString. That's it. So now I've got two things. I've got a definition of the type class. So I have a set of behaviors that I want to implement. And I have an instance for every type that I want to define as being in that class. The third thing that I need is a little bit more boilerplate. And that is I need a way to call that method. And the way that's done in Scala is by an implicit. So I'm actually going to declare another copy of the shows method. And it's going to take an implicit parameter. The implicit parameter is the witness. So this is saying this can only compile if there's a witness that says that the type that I'm calling this on belongs to the type class. Make sense? It's a little bit confusing because I called it shows as well, but that's kind of a convention thing. That's pretty common. There's another way to write this using something called context bounds in Scala. Scala loves syntax, so it provides an alternative syntax as well. So what you can do is you can say A colon and then the type class name. So I can say A must be a show. There must be a witness saying that whatever the A is, it must be in the show type class. And then I can ditch the implicit parameter. The downside to this syntax is that I need a way to actually materialize the implicit parameter out. It doesn't have a name in this second case. So I use a utility method in predef called implicitly to pull that out and then call it. But it's really the same thing. OK, in Scala Z, if you're using the Scala Z library, there's a nice thing that they do there, which is that they pimp a lot of the common type classes for you. So you can actually use dot notation. So you can actually just say 3.shows if you're using Scala, Scala Z, that is. OK, so that seems like a little bit wonky. There's three things that I had to do there. I had to declare a type class. I had to make a type class instance. And then I had this extra boilerplate of the shows method. But actually, I've gained some kind of interesting things here. The first thing that I want you to notice is that I declared this behavior on a type that was already defined. It's part of the standard library. It's int, right? Int knew nothing about this show guy that I just made up. But I was able to add a new behavior to int. And that's actually really powerful. I call that the open world assumption. It's a distinct difference between the type class style of ad-hoc polymorphism and subtype polymorphism that you would normally have with interfaces. Another thing that you can do in Scala with type classes is you get a little bit more flexibility. In Scala, you can actually override the type class instance in a limited scope and then have that alternative definition apply. So what I can do here, this little snippet of code here, I defined an alternate instance for int, for show. And in that alternate instance, I'm counting I'm displaying the integer with a set of vertical pipes, kind of like I'm counting in unary. And if I have that thing in scope and call shows, then what gets used is the other implicit. And so I can essentially tailor the specific implementation of show for any particular type wherever I want. And that's actually a pretty powerful thing. I actually don't. Some of you guys know Haskell pretty well. I don't think you can do that in Haskell, can you? Yeah, you cannot do that in Haskell. So Scala's type classes via implicits is slightly more powerful in that regard. So another thing that I want to point out is that type classes aren't quite equivalent to subtype polymorphism. There's a lot of flexibility that you get from type classes, but there's certain things that are a little bit harder to encode with your traditional subtype polymorphism. And so here's a little bit of an example. This is some hybrid combination of Scala and Java. I don't know quite what it is, but you guys will get the idea. So I've declared my show interface here, like Java style with an interface. And then I have two classes that extend show. And then what I do here is I just make a list of show, a list whose elements are of type show, by making a new array list and putting foos and bars in there kind of willy-nilly. And then I can iterate over that list and just call show on each of the elements, and that'll do the needful. The problem with this is, can anybody see the problem with this if you try to encode this with implicits and type classes? Any guesses? Well, if you think about it, the problem is that each of the types of the elements in here is going to need its own type class instance. And there's really only one available for this container, the array list, right? So there's no way to kind of pair the list, each element in the list, with the correct type class instance. Actually, you can do it. And in fact, I posed this question to Dan, and he actually came up with this ridiculous example. If you look at the slides offline, that not easily at least part is linked, and you can actually look at an encoding of this. But the point is to say not that it's not expressible, but rather that it's extremely awkward. Like most of the things that Dan does. Yeah, no problem. So yeah, if you find yourself trying to do something funky like this, you'll find that this encoding doesn't quite work very well. OK, so that's type classes in a few minutes. And now we can move on to the meat of the talk, which is actually the Typeclassopedia. So what the heck is the Typeclassopedia? It's basically just a set of interrelated type classes that have proven extremely handy for structuring functional code. So when you're a functional programmer, these type classes just happen to be really useful, and you'll run into problems when you're writing functional code, and oftentimes, if you're using these type classes, you'll find yourself able to code your way out with really elegant solutions. The way that you should read this diagram, so I should say that I pimped this diagram totally from the Haskell docs. So there's some artifacts in this diagram that are artifacts of the way things work in Haskell. But the idea is that the solid arrows represent the is-a kind of relationship. So every monad is an applicative, is a functor. Every traversal is a functor, and so on. The dotted lines are used to indicate some other kind of relationship, some other being undefined and not really relevant to this talk. And then the grayed out things represent things that aren't actually in the Haskell standard libraries. But I believe that most of them are in Scala Z. So apply, for example, is in Scala Z. So like I said, these are kind of like functional design patterns. I think if you look back, if you weren't using this stuff, you could probably look back at a lot of the functional code that you've written and see how this stuff applies in very clean ways. And the other cool thing to note about this stuff is that there's nothing magical about these particular type classes. I think in general, people kind of get overwhelmed or discouraged when they read these tutorials because it seems like they're more complicated than they are. I mean, literally, functor is just an interface with one method. Applicative is an interface with two methods. And monad, it's three methods, right? So what could be easier, right? Furthermore, there's nothing really magical in the language about these type classes. So when you're dealing with them, like you can actually use these in any language that's sufficiently expressive. There's nothing preventing you from doing that. There's an asterisk there because there's one exception, and that's around monads and the syntax for monads. I'll talk about that a little bit later. But basically, when you're using monads extensively in your code, monads tend to be a little bit infectious, so they tend to propagate around in your code. And the syntax, the raw syntax for accessing the monad interface is kind of ugly. So a lot of languages will have special syntax for dealing with monads. In Scala, that's a for comprehension. In Haskell, that's like do notation. So like I said, these are provided in Scala Z, which is an open source library. And all of the examples, all of the code snippets in here, they're mostly compilable, and they work against Scala Z7. If you're using Scala Z6, there are some slight differences, but they should be pretty easy to pick up on. And like I said, this is how the Haskell standard libraries define this stuff. There were some mistakes that have kind of been made in the way that things work in Haskell, and so that this doesn't represent perfection. Yeah. Anyway, so in this talk, I'm actually only going to cover three pieces of this Typeclassopedia. I'm going to cover functor, applicative, and monads. So we're just going to go right down the line here. Those, I think, are some of the most interesting interfaces to talk about. And hopefully in the future, I'll be extending these slides and talking about, I think the natural extension from what I'm going to talk about is going into monad transformers. And then I'll probably cover monoid and some other things after that. OK, so let's talk about functors. A functor is really simple. Like I said, it's an interface with, or it's a type class with one method. And the only method that it defines is called map. So what could be easier, right? So the map method looks like this. So this is the way we define. So remember, go back to the type class stuff that I was showing you. This is the definition of the type class. So there's this trait functor. It defines a single method called map, which has 2 type parameters and 2 arguments. It takes an FA, which is a functor of A's, and it takes a function from A's to B's, and it returns an f of B, a functor of B's. So this is very intuitively and very simply doing something like turning a list of strings into a list of ints. That would be an example of this thing. So right, we declared a type class. Now we need to say that certain types belong to that type class, and we'll do that by providing instances. And so here's an instance for option. So we just need to implement map. So we declare a new functor option, and we implement map as follows. So let's just follow the types here. We have an option A, a function from A's to B's, and the result needs to be an option B. Well, there's really only one way to implement this, and there's actually some mathematical depth in that statement. There really is only one way to implement this correctly, at least in a way that applies, that is a true functor. And so what we do is we look at our option, we kind of take it apart. If it was a sum, then we just call f on the value within that sum, and then wrap it back up in a sum. Otherwise, it's just none. And the result is an option B. That's it. One of the nice things that I like about Haskell, even though, like I said, I'm not a Haskell developer, really, is that in Haskell, the type signature is actually different. So first of all, the function name is called fmap instead of map. But also, the arguments are reversed. So you're actually going to get the function first. So it takes the A arrows B parameter first. And then it takes an FA and returns an FB. And I actually really like that because it gives you kind of an intuition into another kind of intuition into what a functor does, right? So think about it this way. Just read the type signature. I hand you a function from A's to B's, or I hand the functor a function from A's to B's, and it hands me back a new function which takes FA's and returns FB's, right? So it's basically lifting the function into this new world from a normal old function into a special functorized function. Does that make sense? A little bit? OK, so a little bit more about functors. It's kind of interesting. This is an interface with one method, and we're going to talk about it for a little bit here. So the idea that this is this gives you the ability to map over things, that idea leads you to some obvious examples, right? Any idea? Throw some out, right? There's lists. What else? What else can you map over? Trees. Oh, good. You can map over maps. Yeah, so that leads you to a bunch of really obvious examples. But let's look at something a little less obvious. Functions. You can actually, functions are actually functors as well. And this is where the Scala gets mildly hideous, mildly to slightly hideous. So I actually had to, so function has 2 type arguments, so I had to partially apply the function type constructor. And so I have a type lambda here to do that. But pop quiz, OK, looking at this definition, I define this in kind of a slightly funky way, but there's a very, very simple concept that this is expressing. Can anybody see it? Can anybody tease it out from the crappy Scala? So I think somebody said it. Yeah, exactly. It's just function composition. So functor as function is just function composition. And again, the Haskell version is way better at elucidating this point, right? So here's fmap. Here's fmap, and it takes here's just the definition of fmap. And I'm just going to substitute in the function type, r arrows a, for fa. And then you can see it right there, right? Like there's your composition. I given an r, this can turn it into an a, chain it into this guy, and you'll get a function from r to b, right? And so this idea of functions as functors, it's actually going to be very useful. It leads to a very useful monad extension. So functions as monad will be the reader monad, and that's going to be very useful. We use that all the time in our own code base. I'll talk about that in a little bit. OK, so as an aside, if you read a lot of these tutorials online, there's like sort of a cottage industry around building tutorials around monads and functors and applicative functors. I'm pretty sure there's a company there somewhere that just makes monad tutorials. Anyway, they all use words like box and computational context, and I think that's a good way to start. So you can start with the analogy of, okay, these things work on, like a monad is a container or a burrito or whatever the hell else the tutorial is working with. But go from the intuition and sort of ditch the sort of like, this works on containers, and try to expand your horizons beyond that as quickly as possible. The analogy is good for starting out, but when you ditch it, things will start making more sense more quickly. OK, more on functors. I love map. It's a great function. I can talk about it forever. So there are additional constraints on functors that actually you need to have in order to have a valid functor. So let's think about this. Let's take list as functor, right? So I need to implement a map. Let's say I wanted to implement map for lists. A valid implementation of that in terms of the types, strictly in terms of the types, would just be return the empty list, right? That would match the types up perfectly. But it wouldn't be very useful, and certainly you as a developer wouldn't want to pass something to a function that was expecting a functor and expect to always get the empty list back. That wouldn't be nonsensical. So there's actually functor laws that prevent ridiculous definitions of map. The first is that if you map the identity function over a functor, you get the original functor, right? So that prevents my ridiculous empty list definition. And then also mapping over a composed function is the same as mapping over each function. You can look at these afterwards. I don't really need to harp on them. The important thing to note is that these laws are not enforced by the type system, obviously. There's really no way to enforce this at the type level. So typically what people do is they'll make an instance for whatever type they have, and they'll write a couple tests demonstrating that the functor laws are held up to. And as an aside, I want to talk about this concept called parametricity. How many of you guys know what this is? You guys have ever heard of parametricity? Cool. Theorems for free. Anybody ever read the Wadler paper? So there's a cool paper on this, and I highly encourage you guys to read it, because I'm really not going to talk about it very much, but I'll give you a brief idea. Benjamin Pierce is a great type theorist, and he didn't say this, but he would if he watched more Spider-Man. With great weakness comes great power. Or a great poet once said, "Mo power, mo problems." But here's the idea. You can actually, based on a type signature, if the type signature is generic enough, you can actually determine behaviors of the functions implementing that type. And so let's imagine we're in a purely functional world, and I have this function called fun. It takes an A and returns an A. So what is this function? Anybody? Identity? Well, what else could it be? Successor? No, it couldn't be successor, right? Because this is a generic type. You don't know anything about the type, so there's no way to know. Yeah, that's actually true. So there you go. So actually, yeah, non-terminating functions match this type signature as well as the identity function. But actually, that's kind of awesome, because all I've done is I've given you a type. I've given you a type, nothing else. And you can tell me that there are only two possible implementations that match this type signature. And that idea generalizes quite a bit. So the idea is, like, the weaker the type signature, the weaker the type class, the more you can reason about its behaviors. And that's actually pretty awesome. So here's an example with functors. So imagine I have a list of ints, and I have a function that uses the functor interface, uses the functor contract, and it takes in my list of ints, or my functor of ints. And I forgot to say that it returns it as well. That's a bug in the slide. But what's foo of x's length? Anyone? Exactly, right? It has to be the exact same thing. Why? Because a functor can't do anything to the length of the list. All it can do is map over the elements, right? So all of a sudden, you have a pretty damn powerful theorem, a pretty damn powerful proof that you can say about this foo method. And that's all because the functor interface is so weak. And this is kind of a useful thing to think about. So when we're going to be talking about applicative functors and then monads, but you're going to be using this in your code, and you'll have a choice. Do I need functor? Do I need a monad? Will an applicative functor suffice? And when you're making that choice, it's often better to just stick with the weaker thing, partially because you can reason about it more. Yeah, so I'm restricting things. I'm cheating a little bit, so I'm not dealing with a language where you can have like null or have side effects. So in a pure functional language, there's no constraints on this type A. So therefore, there's no way to, say, materialize a new A or do any kind of transformation on A's. There's nothing you can do, right? All you can do is return it. You can get pretty far on map alone. So we're finally going to move past map. Isn't that awesome? You can get pretty far on map alone, but sometimes you need a little bit more power. And I'm going to motivate this with a pretty simple example. And the example I'm going to kind of have run throughout the rest of this talk. But here's the idea. Imagine we're building some kind of like web-based calculator, right? So how is this going to work? Well, the user's going to input some strings, and then the back end is going to want to parse the strings and then add them up and return them back. So you're going to want to do simple things like parse the string. And here's a reasonable signature for a parse function. It's going to take a string, and it's going to return option int. Why option int? Because the string might not correspond to a valid option, and we're good programmers, and we realize that null is a terrible idea, so we're going to use option instead of null, right? Cool? OK. So let's try to use this with the functor idea, right? So we're going to try to add 2 parsed integers. So we're going to parse 3, and all we have is map, right? That's the only thing we can do with a functor. So if I try to parse 3, I'm going to want to feed it into another function, and I'm eventually going to want to add. So this is probably a reasonable idea of what I want that to do. But the type of this expression ends up being wrapped in option, right? So I have option int arrows int. And so here's what I've got, basically. I want to add another int to this thing. I have an option int arrows int. So I have a function wrapped up in option int arrows int. And then I have option int, the other option that I parsed, or the other int that I parsed. What can I do with that? You can play around with map all you want, but you're not going to get anywhere. It turns out you actually need a slightly more powerful map operation to deal with this. And that's where applicative functors kick in. So let's add the power that we need to functor. So remember that there's an is-a relationship between all of the type classes that I'm going to be talking about today. So every applicative functor is a functor. So it defines map as well. Right? So in addition to map, it defines a new method, which I believe is pronounced app, because it's from apply. So there's an apply type class which sits above applicative, or which sits above applicative and just has app but not map. Anyway, this new method looks very similar to map, but there's a subtle difference, right? So just as before, it takes the functor of A's, but the f that it takes is wrapped up in a functor, right? So it takes an f of A arrows B, and then it returns an f of B. Seems a little bit funky, but we can actually use this to clean up our last example. Clean up in quotes, because it looks hideous, I think. So yeah, we can use app. We can parse our 3, parse nope, map over that with a function that adds the x and y, and that'll work. I'll get an option int as a result, and it'll do what I want. But that looks pretty hideous. Haskell, things look a little bit better. So this is what this might look like in Haskell. If that still looks a little odd to you, then think about it this way. In Haskell, you can call a pure function just by function name with a bunch of arguments trailing. So if I have a 3-argument function f takes x, y, and z, and I can just call it like that. But here's the idea, and this is where I think the Haskell syntax makes things a little bit clearer. What we're doing is we're taking a pure function, so a function that works on pure arguments, and we're turning it into a function that works on effectful arguments. What do I mean by that? Well, instead of x, y, and z just being pure, they might have side effects, right? So they may fail. They might not be valid integers in the case of option, or depending on what other applicative you're using, you might have some other effect that you're talking about. So basically, in the same sense that as before we were lifting a function from being a pure function to a function in a functor context, here we're going from calling a function on multiple arguments to calling a function on multiple effectful arguments. And I think that's a good intuition for applicatives. When you need an applicative, it's basically when you have a multi-argument function where many of the arguments or some of the arguments have effects. So that's when you need applicatives. In Scala Z, there's a thing called an applicative builder, which makes the syntax a lot less awful, frankly. So it's still kind of backwards in my opinion. So what you do is you have the arguments, and then you trail it with the function, which I think looks backwards in my opinion. And you use this operator here. And on my team, we started running out of names for these things. So we're like, what the hell do we call this thing? It's pipes with an at in the middle, and we decided that we'd call it the Macaulay Culkin. So our chat room is often full we've actually named all the weird Scala Z symbols. So we'll be like, oh yeah, just you need 2 Macaulay Culkins and a big bird, and Bob's your uncle, or whatever. So more on applicatives. So what if some of the arguments aren't options? So let's say some of your arguments are effectful, but not all of them. There's a useful addition to applicative, which basically lets you take a pure argument and lift it into an effect. And that's called point in Scala Z7, and it's called different things. It's called pure sometimes, or return, I think. So yeah, that's this guy here. And what that lets us do is say, let's say I had 3 ints that I wanted to add together. 2 were coming from the web, and 1 was the constant 3. I could use an applicative and then lift that pure constant value into the applicative with point. OK. There's an exercise. You can define the applicative instance for option. That should be pretty straightforward. OK, so now we're going to get to monads, everyone's favorite topic. So like I said, I think there's a cottage industry on creating monad tutorials. And I'm going to try not to fall into that trap. But then at the end of the slides, I probably will fall into that trap, because I think I have no choice. But the problem is basically this. You'll see everyone that writes a monad tutorial, hopefully, understands what a monad is. And they got to that point by reading a lot of other tutorials, and eventually some combination of those things clicked and the intuition made sense to them. But I don't think any particular monad tutorial is like one single monad tutorial is just going to be the light for you, including the one that I'm about to give you. So yes, it is a trap. There's a link here. It's to somebody talking about why monad tutorials are bad. So let's go talk about monads. And I'm going to try to do this in a task-based way. So I'm going to take our calculator example, and I'll try to motivate the use of monads with the same calculator idea. So again, we're going to start with our parse example. And let's change the game a little bit. So what if our input string happened to be an optional query parameter as well? Right? So instead of taking a string and passing that to parse, we have an option string, and we need to pass that to parse. OK, so if all you have is a map hammer, everything looks like a nail? I don't know. I don't know how to finish that, sorry. But if you just try mapping the parse function over this guy, you'll end up with something that looks like option int. And you can't really do anything with that either. So once again, we're stuck. There's a couple alternative definitions for monads. So you could define this in terms of a method called join, but I'm going to do it in terms of a method called bind. So I'm going to add one thing to applicative. So again, this is my type class definition. A monad is everything in an applicative plus this method, which is often written like this, and it's pronounced bind. Again, it looks very similar to map or even app for that matter, but there's a slight difference in the way that in the nature of the function that we take in. In this case, we're taking in an A and returning an F of B. Why is that useful? Well, we can do exactly what I wanted to do on the previous slide. That makes it useful. So in the previous example, so that makes our previous example look like this. You can do params.get x and then bind parse, and that will give you an option int. If you wanted to chain these together, you could, but it looks kind of ugly. So I can do params.get x, bind parse, bind x arrows, make a function here, another bind, map, and we're all good. But that looks kind of unreadable, unless you're a robot, maybe. But there's some syntactic sugar. So remember at the start of this talk, I said there was nothing magic about functors, applicative functors, or monads. This is the one exception. I think without syntactic sugar, monads kind of look a little bit painful. Let's see where the syntactic sugar comes from, yeah? So this is a fairly typical pattern where we have a bunch of nested binds and then a final map. I can actually reformat this. All I've done is added some line feeds, and we can kind of see what that looks like, bind, map, right? And that's exactly what a Scala 4 comprehension is, right? So this is just syntactic sugar for this in many interesting ways. So this is much nicer, I think. So interesting thing. Can anybody kind of explain intuitively what the difference in expressive power is between applicative functors and monads, based on what you've seen so far? Yeah, that's the start of the argument. Applicative takes multiple arguments and then applies them to a single function. But of course, if that was the end of the explanation, then I could counter that by saying, here's my, I could do f of x, y, z here, and that would work fine. So there's something else that's a little bit different. Anyone? Yeah, that's not quite. What I'm trying to get at is look at this. What can you do with this in Scala, right? What does this arrow mean in Scala? Like, throw away all this crap that I've just talked about, but imagine this is just some Scala code that you see, right? You can actually use x on the right-hand side of the next generator. This thing is called a generator in Scala, right? So you can actually chain computations with monads. That's the difference in expressive power. With applicatives, you have one computation at the end, but the computation of the individual arguments to that function can't depend on each other. Whereas with monad, x, y, and z could actually be involved. Like I can use x in the computation of monadic y, and that's totally available because I have x available to me within this. Cool? Makes sense? So here's where I get into trying to do a monad tutorial, which might fail. So here's my stab at providing an intuition for monads. So consider the following monadic code. It's just a 4 with 2 generators, monadic x and monadic y, and then it adds them up. What does this code do? Well, it's kind of a vacuous question because it really depends on what monad I'm talking about here, right? The code here looks almost like imperative code, right? When you look at this, it almost looks like, imagine that this just means semicolon, and you have almost something that looks like imperative Java code. And that's another intuition for a monad. You can think of monads as being a kind of embedded programming language where the monad itself defines, the type class instance actually defines the semantics for that programming language. Sounds kind of weird, but I can make it a little bit more concrete. So let's think about some of the monads that we've seen. Option. So imagine that I told you that monadic x and monadic y were working on the option monad. What would this code do? Well, it would basically execute x. Sorry, we'd compute x and compute y and yield x plus y, but if x was none, then the whole result of the expression would be none, right? What does that kind of have the flavor of? Well, it's kind of like an exception, right? It's kind of like exceptions in imperative code. The only difference is that I haven't actually stored a value with the error, so it's an anonymous exception. The reader example. So what reader does is it lets you defer passing in an argument to for comprehension. Effectively, it kind of looks like a global environment. So you can say that there's some global variable containing the environment, and you can actually instantiate that on some particular environment later. It's a little sketchy because I haven't really talked about the reader monad, but those of you that are a little bit more familiar with reader already can kind of maybe can kind of see that. Or validation. Validation is it's part of Scala Z, and it's kind of like a pimped out either type. But what it gives you, or if you're not familiar with validation, just think of either. What you're getting there are descriptive exceptions, right? So you're actually throwing exceptions, but you're able to actually store an exceptional value along the way. So validation is kind of like the validation monad, or monadic code that uses the validation monad is kind of like a little programming language whose scope is defined by the for comprehension, where the semantics are exceptions. Or a list. There's an interesting intuition for list as a non-deterministic computation. So imagine that monadic x and monadic y are lists. Then what this will kind of do is imagine that instead of a computation that yields a single value, it yields multiple values because it's a non-deterministic computation. Then x plus y will kind of pairwise compute the results of all of those non-deterministic computations. So list as monad, the intuition there is kind of a programming language with non-deterministic computations. And that's kind of actually all I have. I know it's a short talk. I think this kind of sets us up for, this slide kind of begs an obvious question, which is, what if you want a programming language with multiple effects? So what if you want non-deterministic computations plus anonymous exceptions, or a global environment plus exceptions? And the answer to that is going to be monad transformers, and that's where I'd pick up next if I was going to continue on with these slides. So that's all I've got. I want to thank you guys for being a captive audience, and I'll take some questions.